project that I'm working on with, and I'll point out here that we have European and Canadian space agencies as joint sponsors of the project. It's called the James Webb Space Telescope, which is my current interest. And the project is on behalf of everybody who lives here on Earth. All 7 billion people on Earth currently, and all future ones will benefit from the results that we hope to get. So there are about 10,000 professional astronomers in the world, and they will all be using the observatory too. And then we'll tell you what we got. So everyone will participate in that way. So, but stepping back into why do we do this, I'm always very fond of the Declaration of Independence. And I read it to myself every 4th of July, just to celebrate something that people did. But Jefferson wrote in that document about the laws of nature and of nature's God. That's what he said. And then he wrote, we hold these truths to be self-evident, that all men are created equal, that they are endowed by their Creator with certain unalienable rights, that among these are life, liberty, and the pursuit of happiness. So if you're a scientist, you say, well, how did we go from the laws of nature to that? So there's a story, and I would sure like to know how that happened. So we are making a little progress. There's a lot to be found out that we can't ever find out. Okay, so it would be better if I used the microphone? Is that better? Okay, happy to do that. So, is that even better? Okay, so for the recording and everything. So, supposing that there are laws of nature, let's figure out how to go after this. So, one of the great scientists of antiquity was Archimedes, and I like to remind people that he worked for the Defense Department of his day. And here are a couple of his inventions, a giant claw that was supposed to help drown a ship, and also the idea that he worked on was maybe you could set a ship on fire by focusing the light of the sun on it. So you can't. That's been tried. But you can blind the sailors. They wouldn't like it. So, by the way, in ancient times they were already able to make a little mechanism that had gears in it that showed where the planets would be over the course of centuries. And this was something that probably Archimedes' shop made. So people think that the telescope was invented by Galileo, but it wasn't. This is a drawing which says that maybe Leonardo da Vinci invented it. He also worked for the defense departments of his day. I cannot read that diagram to say that it means that he did invent the telescope, but other people that have studied it say yes, he did. In those days, it was not possible to make a telescope based on those ideas. So in 1609, Galileo had a telescope, and he managed to perfect the technology of it. Again, he was not the inventor. And by the way, it was a patent application was submitted in the Netherlands for it, and it was declined. We still have the records of the patent application. So people knew immediately that it had military application. So telescopes and astronomy have had this amazing connection for a long time. These are drawings of the moon made by Galileo. And there's a little diagram of the telescope and how it worked on the lower left corner. Mr. Galileo got into a lot of trouble with his sponsors, which included the Pope, by the way. And for those of us people who are concerned about the connection of science and religion and Galileo's story, should be reminded that the Pope still has an observatory, which is located in Arizona now, and there's a Vatican astronomer, and the Vatican has cosmology conferences from time to time. Another thing to remind people of is that we use a calendar that was developed by Vatican astronomers and sponsored by Pope Gregory. So, just a little bit of history. So, astronomers look back in time. I'm going to tell you some of the story of what we found, but this is the basic method that we use. If you look at something that's far away, you see it as it was. You see it as it was when light was sent to us, and light travels pretty darn fast, but the speed is not infinity, so you really can look back. If you look at the sun, you see it as it was 500 seconds ago, the center of our galaxy as it was about 25,000 years ago, and if you could look all the way back to the Big Bang, it was 15 billion years when I made this chart. No longer the exact number. But anyway, how do you know how far you're looking back in time? You see how far you're looking out in space. So now you have to survey the universe. The top method there is the method of triangles, which is what you would do from high school trigonometry, high school algebra. We've been able to do this for thousands of years. And the Greek astronomers used it to measure the size of the Earth and even the distance to the moon, which they got about right. They tried to measure the distance to the sun and they couldn't do it. Although nowadays, thinking about it, we might have been able to do it, even with their technology. The other method that we use is called the standard candle method, which is basically a geometrical method as well. But if you say, I promise you that these two objects are really identical in brightness, but one of them looks fainter, it's because it's farther away. And this is called the inverse square law. And so now we can survey the distance to everything in the universe if we can figure these things out. So this is the beginning of knowing how far you're looking back in time. We have another toolbox item to tell you about, the Doppler Shift. If you want to know whether something is coming toward you or going away from you, you can measure the colors that are coming out of the object. Now we have a very similar effect with sound waves, and many of you already know this well. It's called the Doppler Shift. If a motorcycle comes up behind you on the interstate and then passes, you will hear the pitch of the motorcycle engine will go down quite a lot. So, and this is the same effect almost. So now we're able to measure the speed of the motorcycle, or equivalently the speed of a star coming toward us or going away from us. So with the motorcycle engine, you don't know in advance what the speed of the engine is, so you don't quite know what to do. But with the stars, we actually have the equivalent of the speed of the motorcycle engine in something that nature gives us. If you spread out the light of the sunshine with a prism to make a beautiful rainbow, and you do it very carefully with the good optical instruments, you will see that some parts of the rainbow are dark. And let's see if my laser pointer will work here. See, it's called an absorption line spectrum here, and so there are certain wavelengths of light that are absorbed by the atmosphere of the sun due to the chemicals and the ions and molecules that are in there. So you say, well, this now, you can tell what was the wavelength originally, and now if you see that it's different in some other star, you can tell the thing is moving toward us or away from us. Of course, this also gives us the opportunity to do the chemical analysis of the sun and of every star, because every different atom or molecule absorbs at different wavelengths. And we've got them all measured here on Earth, so we can tell. So this is then the basis of surveying the entire universe and the history of the universe. And now I want to show you how we've been going at this with bigger and bigger telescopes. So here is an image of 4 giant telescopes that were all sponsored by one guy. George Ellery Hale was the son of rich people in Chicago in the late 19th century, at a time when that was the growth point of the country. That was like the happening place. That's where you would have a World's Fair. That's where every new industry would have its headquarters. So anyway, he persuaded a sequence of different rich people to give money to build these telescopes. The first one in the upper left is the classic Yerkes telescope in Wisconsin, and it's the weather is not so great there. So eventually he got to build reflecting telescopes in California, the 60-inch, the 100-inch, both on Mount Wilson, and then the 200-inch in Mount Palomar. So one guy, taking advantage of the interest of the public and the particularly interested people, was able to raise the fortune that it took to build up new telescopes. So this is one of the reasons why the United States has a huge lead, or did at any rate, in gigantic astronomy projects. By the way, the same guy also helped start the National Research Council and build up Caltech, and was part of the World War II effort against the Axis. So an enormously energetic character, you can guess. Now, a little more history. Here is the guy who gave us quantum mechanics, or one of the two actually. Erwin Schrödinger. He showed us that atoms have waves, wave nature, as well as light waves do. And we have been using these equations ever since, and we know how to do it, but we still don't like it because it's mysterious and strange. But it's the basis of everything that you have in this room. Every chemical functions because of his equations. The electronic devices that we build, we use his equations to figure them out. Anyway, 1925, so it's almost not quite a century. It's 90 years ago that started. Something also happened in 1926. This is Robert Goddard, the same guy that we named the Goddard Space Flight Center for, where I work. He was the first guy to fly a liquid-fueled rocket, which meant that you could control where it went a lot better than you could with the solid-fuel skyrockets that we've had for many centuries before that. Then here are two guys that you might recognize. You'll surely recognize Einstein on the right. He is shown there with George Lemaitre, who is one of the two people who figured out that the Big Bang should be happening. So Einstein gave us the theory of general relativity in 1915, 100 years ago. And Lemaitre said, I know what to do with that. I can figure out how that the universe must be working a certain way. He said the universe must be expanding from something he called the primeval atom. He was the second guy to do that. The first guy was Alexander Friedmann in Leningrad, but he died before he found out that he was right. Anyway, Lemaitre tried to persuade Einstein of this. Einstein said, your mathematics is correct, your physics is abominable. Einstein was sure that the universe had to be infinite in age and could not possibly be expanding. Well, he was wrong, and he was also rude. But at any rate, that happened. By the way, for those of others who are concerned about religion and science, by the way, Lemaitre went to see his boss, the Pope. And the Pope said, well, doesn't this Big Bang story, which it was called later on, support the picture in the Bible? And Lemaitre said, of course, as a scientist, no, it doesn't. But he's wearing his priest's collar there because he was a parish priest in Belgium, as well as having a PhD in physics from MIT. What a guy. So other things that happened in 1928, this is the first radio telescope that we know of. Was built with a number of antennas on wheels in a grassy field. And in those days, all we had for picking them up was vacuum tubes, which you never almost see anymore. But he was able to tell that the sun was sending out radio waves, and so as the Milky Way galaxy that we live in 1928. Well, people did not know much to do with it in those days, because technology had not yet advanced to where you could do anything else. So let's see what happens next. In 1929, this was Edwin Hubble, shown at the focus of the 100-inch telescope on Mount Wilson. He's steering the telescope to make sure that you would get a sharp image of the sky. And in 1929, he gave us this graph, which shows that the universe is expanding. So those dots on there are galaxies, and on the horizontal axis is how far away he thought they are. On the vertical direction, how fast they're going away from us. And you see almost all, except 4, are going away from us. You see there's a trend line there that the speed is about proportional to distance. So if you divide the distance by the speed, you get the age of the universe. So that was the first time we had a measurement, 1929. So some of you see the Big Bang Theory on TV, and you think of it, well, that's fun, and people make fun of the Big Bang Theory as though it's just, quote, just a theory. So as you know, scientists use the word theory to mean something very powerful and complete, not just something we cooked over beer one night. But at any rate, this was the first time we knew the universe is expanding. We were forced into it. Almost everyone was surprised except for Friedmann and Lemaitre, who had predicted this. So Einstein still wasn't convinced, but eventually he was. So what happens next? In 1946, something of some interest for public policy. This is Lyman Spitzer, a great astronomer. And during World War II, he was working with the Rand Corporation to think about defense. And they'd been thinking about many, many things. But at the end of the war, he wrote a memo to the Rand Corporation that said, we should build telescopes in space. And not only that, he anticipated that if you could build a big enough one, you'd be able to point it at a star way out there and say, I see a planet orbiting around that other star. Now, to do that, he figured we'd have to get an asteroid and polish a mirror shape into the rock, and then we could have such a telescope. So we didn't get to do that yet, but we're working on it. 1946, he said that. This is Fred Hoyle, also around 1946. He's the guy that gave the name of the Big Bang to the expanding universe. And you see he's British, because you can see him on the other side of the car. He did not like the Big Bang. He did, in fact, there was a pejorative name that he gave to the expanding universe, and he didn't, anyway, he never was convinced. He died thinking that he was right, that the universe is static. Anyway, something else happened in 1946. I turned up. And I had no idea what I was getting into. So what else happened? In 1948, two people right here in town, Alpha and Herman, were working on calculating the Big Bang. The World War was over. We knew about nuclear reactions much more than we had known before. We could calculate. And so they said, you know, the early universe was hot. The heat that was there then should still be here somewhere. It should have a temperature of about 5 degrees above absolute zero. And they tried to persuade people to go measure, and nobody would. So they predicted it, and they were right. The temperature turned out to be 2.7, but it took a long time to find it. In 54 roughly, this is what astronomers thought we would see. This was Mars with canals on it. So people thought they had seen canals. A lot of astronomers had seen them. We actually now have an explanation for what they probably saw. If you have a high enough magnification with a telescope, what it'll show you is the veins and arteries on the back of your eyeball. So how did they fool themselves? Well, I don't know, but they did. I'm so very sorry those canals are not there. But at any rate, that's when I started to get excited about astronomy, and everybody was hoping. Then 3 years later, Sputnik went up, and the public was terrified. Even though the New York Times had warned them at least 25 times that this was going to happen, people didn't pay attention. So suddenly people realized that this country was vulnerable in a way that they never had felt before, because this is something the United States had not done first. And so I was told in like 5th grade that if in case of a nuclear attack I should hide under the table. And even in 5th grade you can tell that's not good enough. But at any rate, suddenly there were huge amounts of resources available for science and engineering in this country. So it's not like people didn't know this was going to happen, but what were we going to do about it? So, in fact, there was a reason, a good political science reason, why we did not launch our rocket first. If we launched the rocket first, then the Soviet Union could say that we were attacking them by flying over their territory. So we had our rockets and we were working on them, but we didn't launch them first. So as soon as the Soviet Union launched theirs, then we could do some too. So we caught up, but it took us a while. Here is a great radio telescope that turned out was built for purely astronomy reasons. It turned out to be the one that they used to pick up the signals from the Sputnik, and went on to make many, many other scientific discoveries. This telescope is enormous. It's in you can see it's in Britain, near Manchester. Going on a little bit farther into the future. Let's see what my computer will bring up. It's not doing it yet here. Okay. On the left you see the charter of NASA was passed by Congress in 1958, and curiously enough they said NASA should not only exist, but we should tell people what we're doing. We should give out the scientific results. And we're the only federal agency that has that kind of charter. The others should too, but they don't. So next I have Mr. Kennedy. Let's see if he'll speak to us.
Why some say the moon? Why choose this as our goal? And they may well ask, why climb the highest mountain? Why 35 years ago fly the Atlantic? Why does Rice play Texas? We choose to go to the moon. We choose to go to the moon. We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we're willing to accept, one we are unwilling to postpone, and one we intend to win, and the others too.
By the way, he answered the question that many people have, which is, why are we doing this? He said, we're going to do this and everything else that we need to do. He didn't say one or the other, he said and. And it was hard to do. But we indeed did learn how to manage a very, very difficult project. And here is the guy that told him how. This is James Webb that we named our telescope after. He was a born organizer, the sort of kid who would sell lemonade when he was 8 years old, and grew up to be the leader of NASA. And he was the man who went to Kennedy with a plan, which, by the way, is a really important story. He didn't believe his engineers and managers knew the right budget. So in the taxicab on the way to see the president, he doubled the budget request. Can you imagine doing that now with armfuls of PowerPoint and spreadsheets? No, you wouldn't do that. But he realized that you get halfway across the Atlantic and run out of fuel, you're in trouble. So you get halfway through your project and you run out of money, you're in trouble. So he said he better get enough. And it was enough. And it was a fabulous amount of money, and it was enough. So we were able to carry off the project, and in 1969, only 7 years after that speech, we actually landed people on the moon, which is still astonishing to me. So what happened next scientifically? In 1965, this antenna, which had been built for talking to the Telstar satellite, was also used for radio astronomy. Penzias and Wilson were there in New Jersey. They had used this antenna. They said there's extra noise in the receiver. It shouldn't be there. It must come from something. They were not able to prove what it came from, but it turned out that it was from the universe. So that was the heat of the early universe that had been predicted by Alpha and Herman back in 1948. So suddenly we had a whole separate line of evidence that the Big Bang theory is correct. The expanding universe theory is correct. Kept on building more telescopes. This one is a synthetic telescope. You see there are lots of dishes, and they're all connected through these days we connect them through a computer to make a very sharp image of something far away. They found quasars with this one. Quasar is a black hole with stuff falling in. Here's a telescope which again connects to political science in an interesting way. This one is out in Green Bank, West Virginia. A radio quiet zone. If you go there, your cell phone will not work. And it's only a few hours drive from here. It has a reason for being there that's got politics in it. Not only is it a good place for a telescope, but Senator Byrd lived in West Virginia, and he wanted a project to help people in West Virginia have a business. There's not very many natural businesses in West Virginia, but this was one. And so it's a very, very powerful telescope. It works in tandem with this one, which is in Puerto Rico. This is a telescope which is even larger, but it doesn't move. And there's a 1,000 feet across, big concave spherical mirror hanging in a valley in Puerto Rico. And they are able to send out radar pulses with this, which are so powerful that you can bounce them off of Venus and make a map using the pulses that come back to the previous telescope I just showed you. So it's good enough. You can tell if Venus, you can actually map Venus and see that it has a volcano, and that you can tell if that volcano is going to erupt or not from the maps that you can make with this combination of two telescopes. You can even send it all the way out, beam the beam all the way out to Titan, which is a satellite of Saturn, and you get a reflection off the lakes on Titan. Titan has methane, liquid methane in lakes on the surface, and they bounce back. You can pick them up. So totally astonishing things. This was built forever ago. It was very old, and is now in some danger of being closed because the National Science Foundation doesn't want to keep on sending the money. So politics comes into science in a lot of interesting ways. Now I want to show you the thing that Greg was mentioning earlier about the Kobe satellite. This is a satellite that was conceived in 1974 when I had just escaped from graduate school with a failed thesis. And my thesis failed, but I said to my new boss, as I was a postdoc at NASA, my thesis failed, but we should do it in outer space. So he said, we'll get our friends together, we will write a proposal. We sent it into NASA, and NASA said yes. They actually were very surprised. They had 150 proposals back in 1974, and they got to fly at least 12 of them were actually selected. So this was proposed in order to measure the cosmic heat, the remnant of the early universe, and had 3 experiments on board. And the observatory, by the way, is still up there in space. It hasn't fallen down, but we're not using it now. So within a few weeks of launch, we were able to make this plot, which when I showed it at the Astronomy Society meeting here in DC, we got a standing ovation for that plot. So what the plot shows is the Big Bang Theory is probably right. There's this theoretical prediction, which is the smooth curve there, and you see all the measurements are right on the curve. And so it meant that the wrong data that we had before that supported wrong theories, we could ignore all that wrong information that we had before. So standing ovation for that, and I never expected it, because of course I was convinced that was what we would find, but not everybody expected it. So that was our number one result. Number two came a couple of years later, and the thing to map that we've shown here are maps of the sky. And the one to concentrate on is the one in the lower right-hand corner. The whole sky has been measured and flattened out onto an ellipse, just as you would make a map of the Earth. And what we see are hot and cold spots in the early universe. So this was the first detection of them. Now, this was front page news around the world. We had the phones ringing for days about this one. And when Stephen Hawking saw that chart, he said it was the most important scientific discovery of the century, if not of all time. So at first I didn't appreciate why he thought that. I thought he was just being really nice. Now I can tell you why people cared so much. Number one, if those spots were not there, we would not understand why we were here, because with what we know about the universe today, if those spots were not there, we could not exist. Okay, so the way that we think happens is gravity operates on those spots to make some parts of the expanding universe stop expanding and fall back in. So we're here because of those spots. Number two, we now know that most of them come from something called dark matter, which only astronomers can detect so far. And number three, they tell us about the conditions of the Big Bang material, whatever it might have been, if we can ever figure out what they mean. So that hasn't happened yet. But it is our evidence of what was going on in the first sub-microseconds of the expanding universe. So I told you I'd start at the beginning. Well, this is still not the beginning. The question before this one is, well, what made that happen? And nobody knows. There are plenty of stories, and you'll hear words like inflation, which might be true, but we can't prove it yet. So something you would probably think to ask is, where was the Big Bang? Because everybody asks me that. But as far as we can tell, Hubble's plot tells us there is no center. And we have not, as astronomers, ever found any sign that there is a center. So for those of you who are saying, well, where was it? It was that way. It was everywhere. We are inside the expanding universe, and we always have been, and there does not appear to be a center. So I've got the drawing of my three astronomers here, all thinking about who's in the middle. And they would all compute that their race started an hour ago, but there's no grass in outer space. Nobody knows who's moving, so nobody can claim to be in the middle. So anyway, that was drawn from the human perspective, obviously. So that means also I do not have to draw you a picture of the Big Bang. If somebody does draw you a picture of the Big Bang, it is wrong, because you cannot stand outside the universe and draw a picture of the universe. There's no more dimensions that you can imagine going into as yet. And I don't know if we will ever figure a way to do that, but so far not. So what we should be calling it instead of the Big Bang is the expanding universe, because it's an infinite universe expanding into itself. So I told you that we think that it happened because gravity reaching across space is able to stop the more dense regions from expanding and make them fall back in to make stars and planets. So we're here because of that. So this is basically telling you that the universe is structured to be unstable. Gravity makes things unstable, makes things heat up by themselves. So if you're taking basic physics, you hear that things do not heat up by themselves. If you put a warm thing next to a cold thing, they'll come to a temperature in between. If you let a gravitational system run for a long time, it will spontaneously heat up. So it's always a surprise, but this is something astronomers find. So after that goes, then all these other things can go. Now I want to show you another telescope which is finding something even remarkable today. This is another international project. The United States, in partnership with Europe and Japan, have built this gigantic telescope in the desert in Chile. This is at a very high altitude. It's over 16,000 feet up there. If you go there to work, you have to take oxygen with you just in case you really need it. And this collection of dishes is connected by way of computers, and they've made an image of a brand new star in the upper left corner in the process of forming a solar system. So this is exactly what astronomers hoped we would find, and they did find it. So what you see there orbiting around the star in the middle are dust grains that have just the slightest ability to radiate millimeter waves and be picked up by this giant telescope. And you see also that they're ellipses, which we presume to be really circles, just because we're looking at it sideways. And you see that it's not exactly smooth. There are dark regions and light regions, and those are thought to be, the dark regions are where new planets are being formed, and they're soaking up the dust grains. So this is how planets like those in our solar system are thought to have formed. So if that's really so, then we have now seen something like the solar system forming. So another astonishing discovery. It builds on the technological basis of the entire worldwide scientific and engineering establishment. Has more compute power than any other computer in the entire world just to process that data. Another wonderful international project we have started in, and by the way, the United States is not a participant in this one. This is called the Square Kilometre Array. Can you imagine a telescope a kilometer in size? They decided to build this in two parts, one in Western Australia and one in Southern Africa. And in both places they built them where there's no cell phone service, because the cell phones would interfere with this telescope. This is a telescope which is said to be so powerful that if there's a planet out there around a nearby star with an airport radar system, like we have, that we would know. So it seems unlikely to me that we'll pick up airport radars on another planet, but I'm sure people will try. Another thing I want to show you, a connection between astronomy and public policy. If an astronomer wants to get a sharp image of a distant star, well, we have a problem, because we look through the shimmering atmosphere of the Earth. And the atmosphere of the Earth will distort the image that we get, and it will never be very sharp. So you can see this yourself if you look across a hot field in the summertime. The distant grass and trees are shimmering around. Don't like that. So anyway, in the 70s, while I was a graduate student, this idea was invented to measure the shape, measure the distortion of the waves that are coming in and correct them every 1,000 times a second. And maybe you could get a sharper image. So you see that's the diagram on the left. There's a camera and a sensor and a control system to control a little mirror that can adapt to the variations of the atmosphere above. So this was thought about for astronomy. Then it took a few days, I guess, before people realized that this was also good for weapons and for surveillance. So if you have a big telescope and you're in the military, you can do two things with it. One is you can look at things, and one is you can fire weapons, laser weapons with them. So it didn't take very long for this to be classified. So astronomers didn't much know about this for a long, long time, until about 25 years later, when French astronomers reinvented the same thing. And of course you can't classify French astronomers. So now every big telescope in the entire world has this kind of system on it. So we get much, much sharper images than we ever thought we would get before. Now, if you look at the right-hand diagram, you see a very, very similar picture. And this is what you can get if you go to the eye doctor. If you go to the eye doctor and you say, "Doctor, I'm not feeling so good, my eyes are a little blurry," and the doctor says, "Okay, I'll look at your retina, and this is what I'll use. I'll use a camera that uses almost the same mathematics to give me a sharper image of the back of your eye." So it works really, really well. And so many, many thousands of eye doctors have this, and many, many millions of people have had their eyes examined with the same technology. Now, if you're a football star and you need to see better and better, as professional footballers do, then you say, "Then please, doctor, will you fix my eye so I see better?" And so then you do the next step and you transfer the information from what they've got on their adaptive mirror there. You use LASIK surgery to put it on your eyeball. And so people can get 2010's vision from this process. So I understand this is necessary surgery for football stars. Who knew that this would be the sequence of events? Now I want to show you some more giant telescopes and think about what we're learning with them. These are two big telescopes in, in Hawaii on the left, and four very big ones in Chile. These are the ones on the left are about 33 feet across each mirror. The ones in Chile are a little smaller, but they're working together. And this is an interesting thing because we've suddenly been able to make bigger telescopes on the ground using that stuff I just showed you. And now we have higher ambitions. How about bigger and bigger and bigger ones? So we are now in worldwide engaged in 3 even bigger telescopes. One of them is called the Giant Magellan Telescope. It's going in Chile. One of them is called the 30-meter telescope, and it's going in Hawaii on Mount Mauna Kea, a big, not very extinct volcano. And one of them is the European one, which is the biggest. It's almost 40 meters across, which is almost the width of a football field. And they've already blasted off the top of their mountain to start building theirs as well. The one on the left, by the way, the 30-meter telescope. Now this one here is in some trouble because local inhabitants in Hawaii say, that's our mountain, and it's sacred to us. You can't build any more telescopes on it. So you probably have seen that in the news a lot. So now I want to show you a little bit about space astronomy, the Hubble Telescope, and talk about its connection to the defense business as well. Hubble is up there and working. It's 25 years old, and it's working beautifully. It's as powerful as it has ever been. But what people didn't know when we launched this was that there were about 20 equally large telescopes that had already been built for looking down at Earth. And the only reason astronomers and NASA were able to afford to build this one is somebody had already solved an awful lot of hard engineering problems to look down. On the other hand, we were the first ones that really had to have electronic cameras. So the little camera that's in your cell phone that you use every day, the first really good prototypes were something that we built for NASA to have on the first generation of Hubble instruments. So it's up there, it's working beautifully, and as you know, it's working beautifully because we've been up to surface it 5 times with space shuttles and astronauts. So what did we see? We saw this telescope picture. This took 2 weeks to get. This is a picture of something called the Hubble Deep Field, and we just stared in one direction where there was nothing much to look at. And what they found, of course, was thousands and thousands of galaxies, many more than people anticipated would really be there. And we found also that they formed much earlier in the history of the universe than we had thought. So you can't really see it well in this room, but there are lots of little specks on there that are the most distant observable galaxies yet. And they happened within about 1 billion years after the start of the universe. So astronomers wanted to know as soon as they got that picture, well, what happened? How did that happen? So that, of course, led to the request for an even bigger and better telescope. So here is a nearby nebula, and this is like the Milky Way. So you know, each of these things is a collection of more or less 100 billion stars orbiting around a common center. They are held together by gravity. If this were the Milky Way that we live in, the solar system would be located on the outer edge. So I love the picture just because it's beautiful, but also the different colors here tell us different things are going on. Like where stars have just been born. Now here's something that might be a surprise to you. Stars blow up. This is one that blew up in AD 1054 as seen by us here on Earth. It actually, of course, happened a long time before that because it takes a long time for light to get here from there. This is a pretty important part of our history because stars like this blew up and produced the chemical elements that we're made of. When you look around you, you see carbon, oxygen, nitrogen, phosphorus, calcium, all the other elements that you know of. They were all produced, except the hydrogen and helium, in nuclear reactions inside stars. So how did they get back out again? Stars blow up, their material is recycled, And so we are completely recycled. The atoms you're made of have traveled millions of light years already before they got turned into us. So you don't feel it, but you are already interstellar travelers. This is a place observed that you can observe yourself. This is the Orion Nebula. If you go out of town and you have binoculars, you can point at the middle star in the sword of Orion, constellation of Orion, and this is what's there. It's not just a star, it's a whole cloud of glowing material lit up by several really bright stars, and new ones are being born in there all the time. So whenever we get a new telescope, we always point it over there because it's really exciting. We discover new things. For instance, we found in there at least 100 different organic molecules just floating around in the space between the stars. So a few more surprises for you. A Nobel Prize was given for finding out that this diagram is wrong. When the expanding universe was recognized back in 1929, people immediately assumed that because the universe has gravity, it will slow its own expansion. And that was mostly right. And here the sketch is indicating that galaxies are pulling on each other with gravitational forces. So it was mostly right, but it wasn't completely. So in 1998, these folks observed that the universe is actually going faster and faster all the time, and has been doing so for 5 billion years. So they got their Nobel Prize for discovering what we now call dark energy. So it was a complete surprise. The guy in the middle there was the young postdoc who did the work and first found that the stars are too faint way out there, and he had a hard job convincing the others. But eventually he did. So he told me he was the first one to ever ask for a stroller for his baby when he got to the Nobel Prize. Young guy. So we want to wrap up a little bit by talking about the telescope I'm currently working on, the James Webb Space Telescope, named after the same guy that went to John Kennedy with a plan to go to the moon, and a very great honor it is for him and for us as well. Anyway, this is what it looks like. This is a telescope that does not look like any one that you have seen before. It looks more like a solar energy concentrator. And so light comes in from the right-hand side, bounces off that big gold-colored hexagon, is focused in on a smaller mirror, and goes down into the instrument package. So this is a joint project of NASA with the European and Canadian space agencies. It is a huge public policy matter because it's expensive. In fact, about 4 years ago, the project was very nearly canceled by Congress because the budget that we required was more than they had allocated, and it did not look like we knew what we were doing. So they said, well, go make a better plan and tell us what it is, because we don't like this every year you come back and ask for more money. So we made a better plan, and as far as I'm concerned, a miracle happened. They said, okay. So it's now, the United States budget has $8.00 billion to get to launch. So is that a lot of money? Yes. It's even more than it cost us to get the Hubble Space Telescope up there the first time. On the other hand, I hope that we find that it's worth it. And we're certainly working to make sure. So what has it got? It's got cameras and spectrometers on board to take infrared pictures. So infrared is light that you cannot pick up with your eyes because the wavelengths are too long. But it tells us about new things way out there that we can't see otherwise. And by the way, the Europeans are buying a rocket that will take us into space. So we're putting this telescope 1 million miles out into space. This is a diagram of the Lagrange Points. Some of you have heard of the Lagrange Points. These are places where the combined force of the sun and the earth will pull the object around the sun once a year. So the thing could in principle stay in one of those points all the time. So the one we're going to is the number 2 point, L2. It's way out there, 1 million miles farther out than we are. And it means that although we can get there, we cannot send an astronaut these days to fix our telescope if we make a mistake. So now I'll show you the scary movie, because this is what we have to do. We have to have our telescope unfold after launch. First we unfold the solar panels, and then the transmitter antenna. And now we're unfolding the big umbrella, the big, what we call sun shield. It's actually, will take weeks to do this, not a minute. It has to all be done by remote control. So after it's all unfolded, a lot of us will breathe a lot better. Of course, to make sure that it unfolds properly in space, we have to do several things. One is, wherever possible, we have 2 of everything. Where it's not possible, we have review committees and arguments. And we make sure that everything we've ever thought of has been resolved. So this is the only hope you have when you can't go there to fix it. Then after you've done arguing and testing, you test some more. So this will be tested a great deal, has already been tested a great deal before we finally put it together. But it is definitely a tricky subject to get that to really go out into space and unfold properly. So although we are drawing on military types of technology, we are not aware, from my perspective, that anybody ever needed a telescope like this. So that's what it looks like way out there. This is, by the way, how we get it around the Capitol Beltway. There's a special truck with a special carrier that just exactly fits into the C-5 military aircraft. So we drive it around from Goddard Space Flight Center and well after midnight, very slowly. And when we get to the Air Force Base, we drive the whole truck into the airplane. And then we fly it to Texas, and then we undo it. When we get it to Texas, we take the telescope and we put it in this gigantic vacuum tank down there, where we will verify that it focuses properly. Many of you know that the Hubble Telescope was not in focus when we launched it, and it was a terrible, terrible, upsetting thing. But we managed to make lemonade anyway by fixing the observatory. This time we don't have a chance to do that, so we will have to verify before flight that it focuses. So this is a truly enormous tank. By the way, it has history itself. It's a leftover from the Apollo program. So it's on the National Historic Register. When we needed to improve it, to make it colder, we had to go and fill out some paperwork. So now, what are we going to find with this observatory? Well, I'll show you some of the science we hope to get at. We now have supercomputers, so we can now make a movie of how it might have been. So let's imagine that you know what the early universe was like, what those hot and cold spots in the Big Bang were like, and tell the computer, please now simulate what the universe would do. This is like simulating the weather, except starting with a different point, starting with the expanding early universe. So this is what it looks like if the movie will play for us. So what we see here is a piece of early universe rotating in front of our eyes so you can get a sense of the three-dimensional structure. And gravity operating through space is stopping the expansion of certain parts and pulling them back together. And what you'll see is gradually it develops a filamentary structure with galaxies on strings, and then they'll all flatten out to be almost, there's one almost flat surface in here where almost all the galaxies are in the same flat plane, like that. So this is the first time the people who make these programs claimed that they were getting about the right answer. This is something that looks a lot like the universe we see today. Except, of course, from our perspective, you don't get to watch the movie. All you get to do is to get a few frames of little pieces of it. So, by the way, you see the explosions happening there? That's something that happens quite a lot. Our history of the Earth is full of cataclysms and explosions. Not only the Big Bang itself, but stars exploding nearby, black holes forming in the middles of galaxies. Most galaxies have black holes now. And so we're kind of lucky to be here. We may have needed those explosions, so we probably needed the asteroid that wiped out the dinosaurs. But at any rate, pretty dramatic history. Now here we are, the universe is almost 9 billion years old in this picture, and things are beginning to settle down. Curiously enough, this is the moment at which the solar system is formed. And it's not in the movie, but if it were, it would see a relatively peaceful universe compared to what was going before. So that could be a movie that we have to find out if the movie is true. And so it's not so easy to do, but we will try. Of course, you could run the movie on into the far future to see what will happen in the future too. They haven't done that yet. So here is something we will be using. Nature gave us extra lenses for the telescope. You wouldn't have thought that it did so, but it does. Galaxies have gravity, and gravity bends light. And so Einstein told us this would happen, but he thought we'd never find it. But see that little pink arc in the upper right-hand corner? That's a very, very, very distant galaxy that has been magnified for us by the gravitational forces of the other galaxies there. So that'll be a way that we will surely use. We will be looking into places like this, which is called the Eagle Nebula. Stars have just been born inside that cloud, and it makes astronomers annoyed, because although it's very beautiful, you cannot see the stars being born inside. You see how dark it is. And that's because dust grains in space intercept the light that we'd like to receive. And we said, well, what are we going to do about that light? Let's get an infrared telescope. So this is what you see with an infrared telescope on the ground. It's a bit blurrier, but it shows us that the infrared will go around the dust grains and you can see inside to where stars are being born today. So this is another one of our methods to get at our own history. How else do we get at our own history? We'll look at planets around other stars. So this happens quite a lot. If you are properly lined up, then once in a while you'll see a planet go in front of another star. So this is what the Kepler Observatory did. They watched 100,000 stars for several years, and they now have about 3,000 candidate planets from this method. So the star will blink a little bit, and they'll say, aha, I just saw something happen. If it does it again several months later, and again several months after that, you say, now I know how long it takes the planet to go around the star. Now I can calculate how far away it is, how warm it is, and a lot of other things. So this gives us a chance to learn about planets around other stars. And the big surprise for many people was planets are very, 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 very common. There are as many planets as there are stars. And a lot of them are little ones like Earth, and a lot of them are at about the right temperature to be like Earth. So we do not know whether they really are like Earth. That's for the next round. So could you find out? Well, yes, you could find out. If you could build a big enough telescope, you would be able to observe planets as little dots orbiting around their stars. And you'd be able to isolate the light from the planet, and you'd be able to say, does that planet have oxygen? Because here on Earth, we have oxygen because of plants. So it'd be a pretty good hint that there's life way out there. So this is roughly what it would take. Going from the Hubble Telescope in the upper left corner to the Webb Telescope in the middle to something about twice as large is probably what it takes to find out if other planets are alive. So are we going to get to do this? I don't know. But a lot of astronomers think that they would like to do it, and they think that the public would like us to do it. So probably, I'm hoping that it's cheaper even than the Webb telescope because it doesn't have to be cold. So to wrap up, really, people want to know, well, how far can we go? And I say robots. Robots do not have to breathe, and they do not care that much about cosmic rays and hot and cold. So we already have them in everywhere that's very difficult to go. We have them drilling holes in the bottom of the ocean to get oil. We have them drilling tunnels to carry water. We have tunnel-drilling robots for subways. Basically any place that's difficult or hostile or requiring a special delicacy, we have robots. You can even have your gallbladder removed by a robot as long as somebody's driving it from a distance. So people are pretty fragile. We are probably just as fragile as our ancient ancestors. So we do not like vacuum. We do not like cosmic rays. And so that means if we do go to Mars, we have to be in a hurry. So build you a rocket and build it big. But future robots, I think, will come to be very, very powerful and will go wherever they want to go. When I say they want to go, I'm thinking that some robotic intelligence may come. And I don't know how long it'll come, but if you're thinking about public policy, you have to think about what do we do with friendly and hostile artificial intelligence systems. So very long term, what's going to happen to us? Well, we've got a few hundred years before we run out of coal and oil, maybe longer if we decide not to use it all up. The sea level is certainly rising. We have lots of terrible predictions in front of us, but as you know, a curse, if you had offended the gods in ancient mythological times, your curse might be to know the future and be unable to do anything about it. So both Cassandra and Tiresias were mythological characters whose punishment was that. So I'm not going to say that we know what's going to happen. I don't want to get punished by the gods. But many things could happen. If by unluck all the carbon dioxide that we're currently worried about would go away, the Earth would freeze. And we wouldn't like that. It seems unlikely, but it's an interesting, tricky question. In about 1 billion years, the sun is getting brighter and brighter all the time. It will be definitely too warm for us here. We had better move to Mars, or something like that. In a few billion years, that beautiful Andromeda Nebula out there is coming at us, and we will have a head-on collision. But when galaxies collide, the stars do not hit each other. They just go past each other. So it'll be a beautiful time to be an astronomer. In about 5 billion years, the sun will swell up and become a red giant, swelling out to about the size of the Earth's orbit. So we had better figure out space transportation by then and go somewhere a little cooler. Then eventually the sun itself will go out and turn into a little star called a white dwarf. The very long-term future is the universe is supposed to continue expanding and the galaxies will go away and the stars will go out, and people hate this story because we'd like to live forever, I think. On the other hand, nobody knows if this is the only universe and what's really happening way out there. So if you're interested in additional information, there are lots of websites to find out more. There's a little paperback book which you can get from Amazon, and I will be happy to have questions and discussion. So thanks very much for coming. Greg, what's our time frame?
Here we go. 15, 20 minutes.
15 or 20 minutes.
Should be time for questions.
Time for questions.
Have any questions?
About anything.
Hi there, my name is Robert, I'm a freshman. I'm just wondering, so one of the big issues with research and science is, of course, the political aspect, the funding of it. And one of the big things going on right now is the expansion of a private space industry that's hoping to cut the costs of sending things to space and rockets and fuel and whatnot. So I'm just wondering, what are your thoughts on the private space industry like SpaceX, hopefully cutting the cost of space exploration and thus possibly fueling more research than we could before?
Well, personally, I'm thrilled that they're making some progress. And NASA has signed contracts with SpaceX and Orbital Sciences, both to take stuff to the space station, and they've signed contracts with SpaceX and I think Boeing to take astronauts up. So we're now pushing as far as we can into the commercial world where all of these are supposed to save us money and make it easier to go there, and presumably if it's what we want to do, we can go there more quickly and more cheaply and more often. And so the hope is that there is actually some business opportunity besides just funding NASA. Of course, you might think NASA's the big player. We're not. NASA's budget for space stuff is about 10% of the worldwide budget for all space stuff. So we're the ones you hear about. The other 90%, well, some of them you don't hear about because it's classified, secret. Some of it you don't hear about because it's routine. Ordinary commercial data relay satellites and all those things, it's all getting cheaper. Significant portion is for GPS systems. And if you were to calculate the price of all the GPS systems we have, then it's quite a substantial part of the worldwide space budget. Who would have known? So I'm very eager to see the costs come down so we can do more of what people want us to do. More questions?
You talked before about how it's so difficult to bring humans into space because of biological or cost reasons. A lot of people getting excited about a manned mission to Mars. Do you think, is that a valuable undertaking, or is it a waste of time and resources?
Oh, well, I think it's a different, I asked the question a different way. I asked the question, is it an opportunity that people are willing to pay for? I don't like absolute good and bad. I like to see opportunities. So clearly the desire to send people into space and send them way out there has enabled us to start building a big rocket called the Space Launch System, which if we have it, we'll be able to launch better scientific research payloads as well. The telescope I just showed you, this truly gigantic one, would sure be a whole lot easier if we had a bigger rocket. If you want to send a payload out to Jupiter to see if there's life in the ocean on Europa, which is one of the satellites of Jupiter, then definitely better to have a bigger rocket. So actually, you know, people talk as though there's a finite number of resources in the world. They're not. There's whatever we decide to do. And so we can decide to do pretty much whatever we choose. So I don't know what people will choose. Now, if people just want to go to Mars because they want to go, I think that's tourism. If they want to go because they're going to bring back something that's valuable to all of us, then science. And then I think governments should pay. We should collect from the people. If people want to go privately to look around or live there because that's what they want to do, let them pay. That's my sort of viewpoint on that one. But if the costs come down, then they can.
What will be the role of the Hubble after James Webb goes up?
Oh, after the Webb telescope goes up, we'll probably keep the Hubble running. Predicted life is fairly long yet. I think it's not wearing out. So I'm keeping my fingers crossed, etc. But it's working beautifully, and I hope it keeps on going. It doesn't do the same thing. So it does. It can observe at wavelengths, especially ultraviolet, that no other telescope can do. So if it's still running, then we would use it for the things that it can only do.
What is it about the Lagrange point that we want to send the Webb telescope to that prohibits manned missions from doing maintenance and stuff?
Oh, it's just too far. The Lagrange point L2 is 1 million miles out, and so we don't yet have the technology to go there. We could. We could have already been there, but we didn't. So this new rocket that we're building, the Space Launch System, certainly could send astronauts out there, but we're definitely also not ready. The Webb telescope will be launched in less than 3 years, and so I'm sure we will not have astronauts ready in 3 years. There's no reason they couldn't go, but it takes work. More questions?
What are like the ethical aspects of like space? Is that like what you said, making a business out of it, like we don't really own it, and like is that discussed at like NASA? Like the idea of like, I mean, if you make it like a more like non-governmental funded, people are just going to be buying the space and like owning the sky.
Okay, well, it's you're actually touching on a very large subject of space law. People write books about it and have conferences about it, and we have treaties about it. And so there's a process that governs what people can do. Here in this country, we need approvals from the government to be able to launch stuff, because obviously launching something is a hazard for the neighbors if it doesn't work. So there's that. The Congress has just passed a law about if you can bring something home from an asteroid or from the moon, it's yours. So this is a step towards encouraging private enterprise in space. So we'll see how that goes. Right now, nothing of that sort has happened yet. I think it's already agreed by treaty that nobody can own the moon, and nobody can claim other planets either. But things being as they are, we have treaties that people violate too. And people are building up a little island in the China Sea and claiming that it's Chinese now. So it's tricky. And interesting. More questions?
What you said that we have the ability to do whatever, we just have to choose. I mean, obviously, the telescope is one thing, but what's another thing that you personally really want?
Oh,
To choose that?
so she's asking what I really personally want besides another big telescope. I would really truly love to find out if there's life out there. And so a telescope isn't the only one thing to try. So I'd like us to keep on working on the Mars question and keep on sending better robots to see, well, really what's out there. It's a long process, because if you land in the wrong place and you happen to be unlucky, you won't find out that it's alive even if it is. Another favorite place to go is Europa, which, as I mentioned earlier, it's a satellite of Jupiter that has an ocean covered with ice. And some folks in the Congress are quite enthusiastic about this because they recognize that that's a place you should look for life. Now, is that hard? That's incredibly hard, because there isn't even any atmosphere on that satellite to help you land. So you're pretty much on your own. It's rockets or else. And so, anyway, lots of things to find out. And closer to home, there are a million other projects that are also important. I'm also pretty interested in how do we survive for the next billion years. There's a lot of things we have to manage to survive for a billion years, and energy resources and environment are obviously some of them. So got a lot of things to work on in the public policy arena. So for those of you here who are taking on the public policy challenge, I thank you for doing that. It's tricky and interesting, and definitely worthwhile. More questions? Are we wrapping up?
We can take
What made you interested in space?
What made me interested in space? Sort of a happenstance. When I was a high school kid, a college kid, I wasn't that excited about it because I thought the most exciting part of science was particle physics, and we were going to find out about the elementary particles. And so I got led into space by a roundabout method. After my thesis project failed in Berkeley, I thought I'd better get a job. I got a postdoc at NASA. I was going to do radio astronomy. And it was from there that that's where I was when NASA said they wanted proposals. I said, oh, boss, we should try this in space. That's how I ended up here. So it's a little bit of a chaotic process, how you go from place to place. I was not that excited about space while we were doing the Apollo program. Maybe I should have been, but I didn't even get to watch the landing. At that summer, I was a summer camp counselor, and I was putting little kids to sleep at night.
So we know that a lot of funding for this kind of technology has to come from good public opinion. And we also know that a lot of the general population maybe isn't that aware of what's going on or really interested. So what should we do, maybe the government or even the private sector, what can be done to make people more aware of that and maybe more excited about these kinds of projects so that there comes up more in the political sector, in the political sphere?
Good question. That's actually, I wouldn't say we don't have enough money. But we could always do more with more. So I think our job is to tell people how it's exciting and why it matters to other people. So the way I think about it is we're looking at our own history. How did we get here from the beginning, and where are we going to go in the future? And so this is something that touches people pretty deeply. I used to live in New York, and I'd open my astronomy book on the subway, and people would want to talk to me. So I think there's really a great fascination of the public with what we do. This doesn't go real deep in it always because they don't read all the astronomy books, but they just want to know, where are we, where do we stand? And so I think there's a deep interest. We just have to say, you know, we got something. Would you like us to continue?
take maybe one more question. All right.
Okay,
Let's
thanks
thank
very
the
much.
speaker.